Hello everyone and welcome to another video. In the last session we talked about alkali metals and group 7 nonmetals, the halogens. Today we'll talk about transition metals. These are metals found at the middle of the periodic table, in fact as well as below the periodic table. As you can see right here, these are the transition metals, as well alongside the lanthanides and the actinides, as well below the periodic table. All of these are the transition metals. They have the same characteristics as the other metals. They are shiny, ductile, malleable, good conductors of heat and electricity, and they have high melting and boiling points. They are also hard because their atoms are compact. Now, if you're comparing the physical properties of a transition metal and an alkali metal, there are three main differences. First of all, alkali metals are soft, and their softness increases as we go down the group. They have low density compared to the other metals or the transition metals, and they have low melting and boiling points. So these are very important three differences in the physical properties between transition metals and alkali metals. Now to the chemical properties. They are less reactive. Transition metals are less reactive when you compare them to alkali metals, which readily react with oxygen. Transition metals do not corrode, meaning that they do not react readily with oxygen, except for iron. Actually, iron reacts with the oxygen and it rusts easily, right? So that's the exception to this rule. They show no clear trend in reactivity, unlike alkali metals. Alkali metals, going down the group, their activity increases. There is no trend in here in transition metals. They do not react with cold water, unlike alkali metals, which were reactive with cold water. They were forming the metal hydroxide, as we've mentioned before. They have more than one oxidation state, which is a very important difference. They are multivalent. For example, manganese, it has so many oxidation states from +1 all the way up to +7. It can participate in chemical reactions by losing 1, 2, 3, 4, all the way up to 7 electrons, unlike alkali metals, which were monovalent. Their valency was 1. They could participate in reactions by losing 1 electron only. They form colored compounds, which is very important as well, except for zinc. Zinc does not form colored compounds. Now, just to get over the whole colored compounds thing, I need you to note that alkali metals, or all metals actually, let's start just with the metals. All metals have the same color, which is gray, except for two metals, which are gold, Au, and copper, Cu. Gold is golden yellow, as we all know, and copper is reddish brown, right? So all metals, and I'm talking about the metal itself, not its compounds, all metals are gray, except for copper and gold, right? That of course applies to the alkali metals, to the transition metals. Now, the alkali metal compounds like potassium bromide, sodium chloride, all of these compounds are colorless, or they form colorless solutions, right? Their color itself is white, and in chemistry, white is not considered a color. Black is a color, yellow is a color, red is a color, white is not considered a color. So, alkali metal compounds are white and they form colorless solutions. So if you're ever asked about the color of potassium iodide solution, it's colorless. Potassium iodide as a solid is white. Now to transition metals. Transition metals form colored compounds except for zinc. So for example, potassium permanganate KMnO4, that's a colored compound. Zinc compounds are colorless, right? So zinc chloride, zinc bromide, all of these are colorless compounds. So if you are ever comparing between an alkali metal and a transition metal, for example, sodium and manganese, sodium reacts with cold water, manganese does not react with cold water. Sodium is monovalent, manganese is multivalent, or has more than one oxidation state. Sodium compounds are colorless or form colorless solutions, while manganese compounds are colored. But if you are comparing between sodium and zinc, you will use the exact same comparison parameters except for the colored compounds, because zinc forms colorless compounds, right? Now, most of the transition metals react with steam, forming their oxides, right? And we have an apparatus for that. Here we have iron, a solid, reacting with steam H2O gas. It forms iron oxide and hydrogen bonds, right? This is the apparatus for that reaction. Here we have rock still wool soaked in water. It can also be called ceramic wool. The function of ceramic wool is to keep water out of contact with iron, so that just steam will react with the metal sample we have. Right? We just want the steam to be reacting with the metal and not the water itself. Another question you might be asked is to indicate with an arrow where heat is applied. Heat is applied below the ceramic wool because we are trying to evaporate the water and turn it into steam, and below the metal itself because one of the conditions of this reaction is that the metal sample we have should be hot. Another question is that why is hydrogen collected above water? Hydrogen is collected above water because it doesn't dissolve and because its density is less than water, so it can be collected above water. If it was soluble in water, we wouldn't be able to collect it above water, right? The reaction conditions for this reaction is that we need hot iron or whatever transition metal we're using and applying heat, of course. Now to the catalytic activity. So what is a catalyst? A catalyst is, in most cases, a transition metal or a substance added to a chemical reaction in order to decrease the amount of energy required to start that reaction. Some chemical reactions require very high energy, like 1500 degrees Celsius, for the reaction to happen. That's a lot of energy. And it's really hard to provide that amount of energy. And if you could provide that amount of energy, it will be very expensive. And the final product from your reaction will be expensive as well. So we use a catalyst to lower that energy. Like if we add a catalyst to such a reaction, the energy will be something like 800 degrees Celsius, which is way less than 1500. The catalyst is in most cases a transition metal. For example, iron is used as a catalyst in preparation of ammonia by Haber-Bosch process. Vanadium oxide is used as a catalyst in contact process in making sulfuric acid. We'll talk about these two methods in greater details later on. Now, why can't we use alkali metals as catalysts? If you think about it, alkali metals are way more reactive than transition metals. So if you use or try to use an alkali metal as a catalyst, it will react with the other reactants and it will interfere with the product. And one very important condition in catalysts is that they do not interfere with the reaction products. All they do is just lower the energy required for the reaction to happen. Alright, they do not participate in the chemical reaction. And that's why we do not use group 1 metals or alkali metals as catalysts, because they are very, very reactive. This is the comparison I was telling you about. This is a comparison in terms of chemical properties between an alkali metal, sodium, and a transition metal, manganese. Right? Now we'll start talking about redox reactions. Redox reactions are oxidation reduction reaction. So you notice red here means reduction and ox here means oxidation, right? Redox reactions can be defined in two ways, in the terms of loss and gain of oxygen or hydrogen, and in terms of electrons, loss or gain of electrons. For core or year 9 students, they're supposed to learn about the oxygen and hydrogen terms only. Extended students are supposed to know about both the loss and gain of oxygen or hydrogen and the electrons. All right. Here we have copper oxide plus hydrogen to form copper and water. Now, oxidation is defined as the gaining of oxygen or loss of hydrogen. Gaining of oxygen or loss of hydrogen. While reduction is the other way around. It's the loss of oxygen or gaining of hydrogen. Now, if you look at copper oxide right here, here we have copper oxide. In the products, it became copper, which means that copper oxide lost oxygen, which means that this process is called reduction. Now, if we look at hydrogen, it gained oxygen, and gaining of oxygen is called oxidation. So again, loss of oxygen or gaining of hydrogen is reduction. Gaining of oxygen or loss of hydrogen is oxidation, right? The element or the reactant that loses oxygen or that goes through reduction is called an oxidizing agent, and the element or the reactant that goes through oxidation is called a reducing agent. Right, you just flip the rules. Copper oxide was reduced into copper, so it is an oxidizing agent. Hydrogen was oxidized, so it's a reducing agent. Okay, so the gaining of oxygen or loss of hydrogen is oxidation. The loss of oxygen or gaining of hydrogen is reduction. Copper oxide turned into copper. It lost oxygen, so that's reduction. Hydrogen, so copper oxide is an oxidizing agent. Hydrogen gained oxygen, so it was oxidized, so hydrogen is a reducing agent. Now we have this experiment right here where we reacted copper oxide with hydrogen. You need to make sure that hydrogen in this hydrogen right here, it has to be very, very dry, right? You have to pass it by a drying agent like sulfuric acid. Sulfuric acid is a drying agent. It absorbs the water, right? Why is that? Because if you noticed, the products of this reaction are copper and water. So we need to make sure that the water formed is due to the reaction between copper oxide and hydrogen, right? Now let's take another example on the oxidation and reduction. Okay, here we have iron oxide plus carbon monoxide. This reaction would yield iron and carbon dioxide. We want to determine the reduction, the oxidation, which one is the oxidizing agent, which one is the reducing agent, right? Okay, now let's start with iron oxide, Fe2O3. It ended up becoming just iron, which means that it lost oxygen. Loss of oxygen is called reduction, all right? So as we are here, that means that iron oxide is the oxidizing agent. As for carbon monoxide, it gained more oxygen. Gaining of oxygen is called oxidation, which means that carbon monoxide is the reducing agent. Here's another example. The reaction between hydrogen and nitrogen to produce ammonia. Nitrogen gained hydrogen. Gaining of hydrogen is called reduction, which means that nitrogen is the oxidizing agent, or it can also be called oxidant. While hydrogen, instead of being pure hydrogen, was the highest percentage of hydrogen, it now has nitrogen, which means that the overall percentage of hydrogen decreased, meaning that you can say that it lost hydrogen, which makes this oxidation, meaning that hydrogen is the reductant. Another example, and this will be our last example in explaining oxidation and reduction in terms of loss and gain of oxygen and hydrogen, the reaction between hydrogen and oxygen to make water. Here, hydrogen gained an oxygen, which means that this is oxidation. While oxygen, instead of being pure oxygen, it lost the percentage of oxygen decreased, and now it's attached to two hydrogen atoms, so you can say that it gained hydrogen, which means that this is reduction, making oxygen the oxidant, while hydrogen is the reductant. A final note is that oxidation is an increase in the overall percentage of oxygen, while reduction is a decrease in the percentage of oxygen. An oxidizing agent is the substance that loses oxygen, and a reducing agent is the substance that gains oxygen. Okay, that in terms of oxygen loss and gain. Now let's explain redox in terms of electron loss and gain. Sodium has the electronic configuration of 2, 8, 1. In chemical reactions, it loses one electron to become a sodium cation. The process of losing electrons is called oxidation. Chlorine has the electronic configuration of 2, 8, 7. In chemical reactions, it tends to gain one electron, forming a chlorine anion. The process of gaining electrons is called reduction. As we've mentioned in oxidation and reduction in terms of losing and gaining electrons, the substance that goes through the oxidation process is called a reductant or a reducing agent. The substance that goes through the reduction is called an oxidant. You can always remember this rule, that oxidation is loss of electrons and reduction is gaining of electrons through this mnemonic: oil, rig. Oxidation is loss of electrons, reduction is gain of electrons. Now let's talk about oxidation states in greater details. First of all, you need to differentiate between the way of writing an ion and writing valency and oxidation state. For example, this is sodium. A sodium ion will be carrying a positive charge. If you want to talk about the valency of sodium, it's equal to 1 without adding any charge to it. The oxidation state is positive 1. Okay, you write the charge and then the number, not the other way around. Calcium 2 positive. While writing the ion, you write the number and then the charge. The valency is just a number 2. The oxidation state is positive 2. Same applies when we're talking about a non-metal, for example, chlorine. Chlorine anion carries a negative charge. The valency has no charge, so it's just 1, and the oxidation state is negative 1. There are some very important rules that you need to be aware of. Rule number 1, the oxidation state of any element is 0. Rule number 2 is that the oxidation state of a compound is 0 as well. This will come in handy when we are writing half ionic equations and ionic equations, when you have to determine if the oxidation state was increased or decreased. So for example, a compound like sodium, an element like sodium. Sodium in its atomic state has an oxidation state equal to 0. Sodium chloride, the whole compound, has an oxidation state equal to 0. Bromine molecule has an oxidation state equal to 0. In many cases, you may be required to calculate the oxidation state of a certain element in a compound. Do not just jump into the periodic table and start making assumptions about the oxidation state of that element. For a matter of fact, many elements that we know can actually have different oxidation states in their compounds, as you will see right now. For example, calcium sulfate. We need to calculate the oxidation state of sulfur. We know for sure that calcium is a group 2 element, so it has an oxidation state of positive 2. So calcium is positive 2. Plus sulfur is our unknown element. Plus we have 4 oxygen atoms. Each oxygen atom has an oxidation state of -2. This is an ionic compound. As an ionic compound, has an oxidation state equal to 0. Math-wise, you can conclude that sulfur has an oxidation state equal to positive 6. Another example. Here we have manganese oxide, and we want to calculate the oxidation state of manganese. Manganese is our unknown element. Oxygen we have 2 oxygen atoms. Each oxygen atom has an oxidation state of -2. The whole compound has an oxidation state equal to 0, meaning that manganese has an oxidation state equal to positive 4. Don't forget the charge, and make sure that you write the charge before the number itself. Here, oxidation is the loss of electrons, while reduction is the gain of electrons. An oxidizing agent is the substance that gains electrons, while a reducing agent is the substance that loses electrons. Some examples of redox reactions are respiration, rusting, and burning. All of these are redox reactions. If we are to draw a timeline or a representation of reduction and oxidation, here we have 0, and then you have positive 1, positive 2, and positive 3. While here we have negative 1, negative 2, and negative 3. If the oxidation state is increasing, meaning that it's going from left to right, this is called oxidation. If the oxidation state is going from right to left, meaning that the oxidation state is decreasing, this is called reduction. As we already know, all metals tend to lose electrons, meaning that all metals are reducing agents, which means that they go through oxidation in a chemical reaction, while all nonmetals tend to gain electrons, meaning that they are oxidizing agents, which means that they go through reduction. That would come in handy if you are in a hurry in a test and just want to identify the reducing agent and the oxidizing agent real quick. All metals lose electrons, which means that these metals are reducing agents and they go through oxidation, while all nonmetals gain electrons, meaning that they are oxidizing agents and go through reduction. Now let's talk about writing half ionic equations. If we have an equation like this one, zinc plus copper sulfate to form zinc sulfate plus copper. This is a solid, this is an aqueous, this one is an aqueous, and this is solid, zinc. Alright, now let's try to write the half ionic equations. Here we have zinc. It's a metal, which means that it will lose electrons. Zinc has a valency of 2, so it will lose 2 electrons, forming a zinc cation, 2 positive. This process is called oxidation, because this is losing or loss of electrons. As for copper, it's present here in the reactants as an ion, because this is an ionic compound, copper sulfate, it's a salt. So this is copper carrying 2 positive, so that is how it exists in this ionic equation as an ion. It will gain 2 electrons, forming solid copper. It's an element, so its oxidation state is 0. Gaining of electrons is called reduction. Okay? Now, if you notice that the amount of gained electrons equals the amount of lost electrons. So now we can write the full ionic equation. These lost 2 electrons were gained here. We are just adding these 2 equations, so you can just put a plus sign here. Minus 2 electrons plus 2 electrons equals 0. Now we write the full ionic equation as follows: zinc plus copper 2 ion. Our products are zinc ion plus solid copper. These 2 are the half ionic equations, and this one is the full ionic equation. Now what about the sulfate ion? As you can notice here, this is copper 2 positive, and this is sulfate 2 negative. Here we have zinc 2 positive and sulfate 2 negative. as you can notice, there is no change in the oxidation state of the sulfate ion, meaning that the sulfate ion will not be making it to the half ionic equations or the full ionic equations. The sulfate ion in this case is called a fixator ion. Now, if we are conducting this experiment in lab, what do we notice? First of all, zinc, just like all other metals, is a gray metal. Here, it turned into an aqueous, so the gray metal will disappear. So that's the first observation. Next, we have a solid of copper. Copper is one of the two metals that we've mentioned that has a different color than gray. It's reddish brown, which means that a reddish brown metal will form, or a reddish brown color will be observed. The third observation is that copper sulfate, we know for sure, is that it's a blue solution. Zinc sulfate, as we've mentioned, it's the only transition metal that forms colorless compounds, which means that the blue color will fade or disappear. So again, the three observations we get from this experiment are: number one, the gray solid disappears. 2, a reddish brown color appears. The third observation is that the blue color of solution fades. We don't give any names, we don't name the compounds, we don't name the precipitates or anything, because it's just an observation. You just mention what you see in the lab. You don't see copper, you see a reddish brown color or a reddish brown precipitate. You don't see zinc disappearing, you see that the gray solid disappears. You don't see that copper sulfate becomes zinc sulfate. No, you see that the blue color of the solution starts fading or turning into colorless. Now let's take another example. Here we have chlorine plus potassium bromide. We've mentioned that experiment before in the last session. This is a displacement reaction, and it's also a redox reaction, as we will see right now. Of course, chlorine is more reactive than bromine, which means that it will displace it. So here we have potassium chloride and bromine. We have 2 here, and we have 2. KBr, it's an alkali metal solution, so that's aqueous and it's colorless. Another salt, aqueous, and bromine is a reddish brown liquid. Now, let's write the half ionic equations. Feel free to pause the video and try to write them for yourself, and then you can check your answer. Here we have chlorine, oxidation state of 0 because that's a compound or a molecule. It turned into chlorine negative, or 2 chlorine negative, right? Which means that chlorine gained 2 electrons. Each chlorine atom gained 2 electrons. Gaining of electrons is called reduction, meaning that Cl2 or chlorine is an oxidant or an oxidizing agent. In the reactants we have bromine or bromide ion here, carrying a negative charge, and we have 2 of it. And in the products we have Br2, 0. The change of oxidation state from -1 to 0, that's an increase in oxidation state, meaning that this is oxidation, which means that the bromide ion lost 2 electrons. Each bromide lost 1 electron, so we have a total of 2 electrons lost, and this is oxidation, meaning that the bromide ion is the reductant or the reducing agent. Now let's write the full ionic equation. Just add the two equations together. Plus 2 minus 2 will cancel each other. Here we have chlorine plus 2 bromide ions. This reaction will yield 2 chloride ions and bromine. Right? In this reaction, if you look at potassium, positive 1, bromide has negative 1. In the products, potassium still has positive 1, while chloride has negative 1. What I mean is, potassium did not change its oxidation state, which means that potassium is a fixator ion. Our observation for this reaction is as follows. First of all, the colorless solution turns into a reddish brown solution. This is the sole observation in this reaction. You might be asking, shouldn't we say that the yellowish green color of chlorine will disappear or something like that? No. Chlorine, in this reaction, chlorine is actually put in a container, a double container, so you don't really see the color of chlorine. What you notice is the color of the solution, because that's what you actually see in the beaker. The colorless solution, because of the KBr, will change into reddish brown due to the formation of bromine. Of course, you don't mention the bromine, you don't mention the potassium bromide. Your observation is that the colorless solution turns into reddish brown. As you can notice from this reaction, that nonmetals are oxidizing agents. So, to modify the rule that we have mentioned before, here, when we said that all metals lose electrons, meaning that they are reducing agents, and all nonmetals gain electrons, making them oxidizing agents, we can add the following. Metal ions gain electrons, making them oxidizing agents, while nonmetal ions, we're talking about the ions here, lose electrons, making them reducing agents. You can apply that to the reaction we've just had right here. As you can see here, this is zinc, it's a metal, it lost electron, so it's an reducing agent. This is copper ion, so that's a metal ion. It gained an electron, meaning that it's an oxidizing agent. Now to the nonmetals. Here we have chlorine as a nonmetal, not an ion. It gained an electron, meaning that it's an oxidant or an oxidizing agent. While a bromide ion, that's a non-metal ion, it lost an electron, meaning that it's a reducing agent or a reductant. Now let's take another example. Iron plus oxygen forms iron oxide. Here we have 2 and we have 3 oxygen atoms and 4 iron atoms. Let's try to write down the half ionic equations. We have 4 iron atoms with an oxidation state equal to 0. In the products, we have 4, because that's 2 multiplied by 2 iron ions. Now, what is the oxidation state of iron in this product? On the margin, right here, let's think about it. We have Fe2O3. Just inverse the number of atoms right here, which means that 3 is the oxidation number of iron and 2 is the oxidation number of oxygen. Remember when we discussed writing the molecular formula for compounds. We said that if we have iron oxide, we have iron and we have oxygen. Iron has an oxidation state of +3, while oxygen has an oxidation state of -2. Scissors way, we end up having this compound right here, right? The Fe2O3, which means that iron has an oxidation state of +3. You can do it this way, and I find this way faster, or you can spend some time calculating it, and you will end up with the same result. Here you have 2 Fe plus, you know the oxidation state of oxygen, 3 multiplied by -2. It's an ionic compound, so the sum for all of that will be equal to 0. From here, 2 Fe will be equal to +6. 3 multiplied by -2 is -6. -6, you send it to the other side with a different charge, so that's +6. Now the oxidation state for iron itself will be +6 divided by 2, which is +3. Okay, now back to writing the half ionic equation. Here we have 4 iron ions with an oxidation state of 3 positive. This is an increase in oxidation state from 0 to 3 positive, which means that this is an oxidation and that iron lost electrons. The question is, how many electrons did iron actually lose? Well, if a single iron atom lost 3 electrons, then 4 iron atoms will lose 12 electrons. Again, this iron atom here lost 3 electrons, forming an iron cation carrying 3 positive charges, right? So a single iron atom loses 3 electrons, which means that 4 iron atoms will lose 12 electrons, math-wise. Now, do the reduction. We have 3 O2 0, and on the products we have 6 2 here multiplied by 3, so we have 6 oxygen ions. Oxygen, as we've mentioned, has an oxidation state of 2 negative. We've calculated it. We know how to find the oxidation state now, so that's 2 negative. So how many electrons did oxygen actually gain? If a single oxygen atom gains 2 electrons, forming an ion carrying 2 negative charges, we have 6 oxygen atoms right here. 3 multiplied by 2, so now we have 6 oxygen atoms. How many electrons will it gain? Scissors way, in here you'll find that 6 multiplied by 2 divided by 1, so we have 12 gained electrons. So here we have 12 electrons. Okay, you can make sure that your calculations are correct by checking that the number of lost electrons equals the number of gained electrons. Now let's write the full ionic equation. Just the sum of these two equations. Here we have -12 and +12, they will cancel each other. We have 4 iron atoms plus 3 O2 to yield 4 iron cations, 3 positive, and 6 oxygen anions carrying 2 negative. So this is the full ionic equation. And as you can see, iron is a metal. It lost electrons. Oxidation happened, so it's a reductant. Oxygen here is a non-metal. It gained electrons, so reduction happened, so it's an oxidant. We are still following the exact same rules. These are the exact same things that we were talking about. These are some examples that you can apply to check your understanding if you can calculate the oxidation state of any element in a compound. These are some very, very important color changes in a redox reaction because of the change of oxidation state. Acidified potassium dichromate. Acidified means that in the chemical reaction we add drops of sulfuric acid, right? This reaction will not happen without the sulfuric acid. Why is that? You learn about in the AS, not in the O level. But acidified, for now, just know that acidified means that we are adding a strong acid like sulfuric acid, right? Acidified potassium dichromate is an oxidizing agent, right? Which means that it goes through reduction. If you try to calculate the oxidation state of chromium cation in this compound, it will be 6 positive, positive 6. The oxidation state will be positive 6. The color of chromium in this oxidation state is orange. When it's reduced, meaning that it gains electrons, so this oxidation state is reduced to 3 positive, the color changes to green. Acidified potassium manganate, KMnO4, is an oxidizing agent as well, with a purple color. The colors, again, are very, very, very important. When the oxidation state changes from positive 7 to positive 2, which is more stable, of course, the color changes from purple to colorless, right? So manganese 7 positive, or manganese from oxidation state positive 7 is purple, and manganese with an oxidation state of positive 2 is colorless. Now, iodine is an oxidizing agent when reduced to iodide, right? So here we have iodine. It's a nonmetal, oxidation state of 0. It has a color which is dark brown. When it gains electrons, it turns into an iodide ion which is colorless. So if in a chemical, if in an experiment the color of iodide changes, that means an oxidizing agent is present in this reaction. Like in this example, hydrogen peroxide, H2O2, is an oxidizing agent. It's a very strong oxidizing agent. If we want to make sure that it's an oxidizing agent, we add it to Ki, and the whole reaction is acidified with H2SO4. The final products are I2, which is dark brown. So the formation of a dark brown color means that there's a redox reaction that has happened, that H2O2 is a strong oxidizing agent, and that Ki lost electrons and formed iodine, which means that dark brown color will form. Some of the common reducing agents are hydrogen, carbon monoxide, sulfur dioxide, carbon itself, and potassium iodide. These are very, very common reducing agents, right? As we said, a nonmetal ion is a reducing agent because it tends to lose electrons, right? Now, these are just final notes. All nonmetals are oxidizing agents. The strongest two are fluorine and chlorine. Oxidizing agents means that they go through reduction, which is gaining of electrons. All metal ions and the hydrogen ion, not hydrogen itself, hydrogen ion, are oxidizing agents as well, meaning that they go through reduction and gain electrons. All metals are reducing agents, which means that they go through oxidation, which means that they lose electrons. The strongest one is cesium at the very end of group 1. All nonmetal ions are reducing agents as well. Okay, like iodide ion, for example. Now we are done with this topic. Thank you so much for watching. You'll find the notes and classified on our Telegram group. You'll find the link for the group in the video description. Don't forget to subscribe to the channel, share the video with your friends, and I'll see you in the next video. Take care.